Welcome to my talk, which presents a motion planning framework for manipulators operating in human-centered environments. My name is Jonas Wittmann and I am a research assistant at the Chair of Applied Mechanics at the Technical University of Munich. The motivation behind this work are shared work cells between humans and robots like the one shown on this picture. In these scenarios, the main components of the environment are mostly static, and occasionally dynamic obstacles or human interaction requires more sophisticated planning approaches. To apply the presented framework, the robot needs to be equipped with joint torque sensors that allow the estimation of external forces. The basic idea of the presented framework is to shift computational effort to the offline calculation phase by generating an efficient environment representation within the map, which in turn results in faster online motion queries. The task that is assigned to the manipulator consists of reaching a fixed pose formulated in the robot's task space with a feasible trajectory respecting its kinematic and dynamic limitations. This figure shows a two-arm manipulator operating in 2D whose task is to reach a specific x1 coordinate, that is to say, the red line. The planning, however, is done in the robot's configuration space, which is shown to the right. Our framework splits this task into three distinct hierarchical phases, which are executed on different time horizons. First, a map is generated offline that efficiently represents the static part of the environment. In a second step, online motion queries find a feasible path using A* search. The path is then forwarded to an online trajectory generator that adapts the motion depending on dynamic obstacles and external disturbances. This work contributes to an existing planning framework with an extended PRM planner that uses obstacle-related sample rejection strategy called ORSR-PRM in the following, and a real-time trajectory generation submodule. As indicated previously, the objective of the ORSR-PRM is to shift computational effort to the offline calculation phase. Here we see the already presented task space of the two-arm manipulator. The corresponding planning map generated with the classic PRM is shown on this picture. To the right, the generated map of the presented ORSR PRM. By adding a sample rejection step to the construction phase, the map generated by ORSR PRM is less dense than the one generated by the standard PRM, which results in faster online motion queries. An efficient representation of the free static task space in the robot's configuration space is ensured by an increased via point density near obstacles. The applied rejection strategy uses the closest distance between a sampled configuration and the obstacle as a rejection criterion. An additional bounding box in C-space ensures a sufficient exploitation of the robot's null space and limits approximation errors. We implemented optimization objectives both for minimal traveling length and for minimal joint torques due to the gravitational load for the online motion queries. The paths resulting from the A* search are then forwarded to the real-time trajectory generation submodule, which computes the reference joint velocities. Therefore, appropriate potential fields are formulated for the various of tasks like reaching the next waypoint. The resulting torques are applied to a virtual system whose mass matrix is scaled such that the calculated reference joint velocities exploit the dynamic limitations of the real robot. Besides the torques due to the potential field formulation, estimated external torques based on proprioceptive sensor information in the dynamic robot model are fed back to the virtual system such that the real robot can react to human interaction. This figure shows the trajectory in C-space of the introduced two-arm manipulator for a motion with 4 via points. The generated trajectory exploits at each time the dynamic limits of the real manipulator either on velocity or acceleration level. We evaluated the framework within a pick-and-place scenario shown on this picture. The robot has to pick items out of the box and place them onto a wooden surface. Therefore, it has to navigate through the narrow passage formed by the two profiles. The right picture shows an exemplary roadmap with 200 waypoints for the scenario, generated with the ORSR PRM. The orange dots indicate the nearest points to a static obstacle for each roadmap configuration. This table shows the computation times for the map generation and path search of classic PRM and ORSR PRM. More than half of the 80,000 generated free space samples are rejected by the described strategy. For the path length optimization objective, the construction time of the roadmap of ORSRPRM is higher compared to classic PRM, as the computational costs due to the additional post-processing rejection step predominate the computational savings due to less samples in the roadmap. It has been expected that the computation time for online motion queries decreases significantly by rejecting configurations that do not contribute to the roadmap quality. This expectation is met by the experiments in which the ORSRPRM showed an average a nearly 3 times faster computation time for the path length objective for a target configuration in 100 repetitive online motion queries and a nearly 5 times faster computation time for the gravity objective. Within the provided video, we demonstrate the application of the framework to dynamic scenarios with human interaction. It is shown that the real-time trajectory generation module leads to an intuitive behavior of the robot that, despite the human disturbances, successfully finishes its pick-and-place task. In this work, we presented a motion planning framework to allow the operation of a manipulator in human-centered environments. A new sampling-based planning approach, the ORSRPRM, as well as an attractor-based online trajectory submodule were introduced. By generating an efficient representation of the free task space in the generated roadmap, we get up to 5 times faster motion queries compared to classic PRM. The limitation-aware attractor dynamics ensure kinematically and dynamically feasible joint inputs even in the presence of dynamic obstacles or human interaction.